I put in an extension request for this most recent exam. I don't think I'll need it anymore.
No, you still have it.
So
You still have it. Happy Tuesday, everyone. You should have received an email. What was it? Beginning of March, end of February. Just in case you didn't see it, or you forgot, final exam is scheduled for May 2nd, 5 to 7. Happens to be a Tuesday, and before my Calc 3 final, which makes me sad. I'm gonna do Calc 3 first, but oh well. Maybe I'll switch it up and give you guys my Calc 3 final. See how you do. We are starting geometry of the plane. I am skipping problems on conic sections for one reason. When I made up the videos, I was too lazy to do it. I don't feel like going back to do just one video, so. Oh well, read the book, read that section on conic sections. You're not going to be tested on it, but just read it. Technically, it should be done in pre-calculus, but there you go. What we will look at is parametric equations and polar coordinate system. Starting with parametric equations. Now, why they even bother doing parametric equations instead of just jumping right into two vectors, I do not understand, but that is essentially what we're doing, is vectors. The idea is simple enough. What's that function? Trick question. There's no function. Not a function. But it is still a curve in the plane that needs to be described. This is the idea behind parametric equations. In fact, for this one, I'm just writing in vector notation. They use parentheses. I'm just going to use braces. It's a freaking vector. Depending on the radius of the circle, all right, so big R. There's the parameterization of a circle. R cosine theta, R sine theta, where theta goes from 0 to 2 pi if you're doing one full revolution. This, of course, means that this curve has a direction called an orientation. Specifically for this parameterization, the orientation is counterclockwise. So we represent that. Just by drawing arrows on the curve. Right. That theta is called the parameter. All right, a lot of times T is used to be the parameter, right? And this is purely because in physics, motion is a function of time. I don't really like T for circle. Oh no, cosine of T just doesn't look right to me. Cosine of theta, it does. So I just use theta. But it doesn't matter, right? It's a dummy variable. Use whatever you want. What this does is this explains, given any theta, we can determine the point on the circle. We can determine exactly where we are. Right? X is equal to r cosine of theta. Y is equal to r sine of theta. It's another way you could write it. That is called a set of parametric equations. Depending on the situation, I will use either notation interchangeably. This is split into two problem sets. The first problem set deals with plotting parametric equations. The second is going to deal with, well, we have something new. So we do calculus on it. And that's what the second problem set deals with, the calculus of parametric equations. Like that, but whatever. 4 cosine t, 2 sine of t. Oh. Ah. I don't know if I actually copied the whole problem. Over 3 domains. Do not know about the TI-89, but the Inspire can do parametric equations. So it can do a parametric plot. And obviously Mathematica can. I will show you how to do it on the calculator, and then I'll be specifically using Mathematica. Because the Inspire cannot draw an orientation. Whereas if you're clever with Mathematica, it can. Control 0. Get over to graph. I'm going to do menu 3, which is graph entry, and number 4, parametric. For cosine of t, or sine of t. And do 2 pi. Oh, I don't know. Let's say the step is pi over 4. You're right, it is 2 sine. That's going to make a huge difference. Enter. What the hell's going on there? Oh dear, that's not right. What's going on?
What is T-step supposed to be in the?
So it's kind of like the X scale, Y scale. How much am I going to step t by each time? And I'm wondering if that's what's causing that. It shouldn't. What happens if I change the step to pi? That is what's causing it. So they had 0.13. I'm going to go back to 0.13 and see what that does. I'm missing now a little bit. Oh, I'm going to go. It's still not giving me the complete picture. That is really aggravating, and I don't know why it's doing that. Oh, yes, I do. It's approximating 2 pi is 6.28. Fixed. Not the best. But if you're in a hurry, you don't feel like going to your computer to load up Mathematica, it gets the job done. And now we say goodbye. Because Mathematica is clearly the superior option. I'm going to use the parametric plot command. Notice in the list it's given parametric plot 3D. That's for Calc 3. Remember, I said this is a prelude to Calc 3. Calc 3 starts with expanding what we're doing now into 3 dimensions. We now need to enter the vector. Put in braces, and then it's just whatever the x is and then whatever the y is. Actually, I am going to adjust something. All right. Then I need to put in the parameter domain. Yeah, I'm doing lines I'm doing arrows as well, so I can't do a function. We wanted first 0 to 2 pi. And that is all you need. That's the minimum. Of course, we can add options to it. When plotting stuff for Calc 3, labeling the axes is pretty much a needed. So I just kind of got used to always putting axes labels. So want. I'm not a fan of the default Mathematica color. And so I always change it. I don't know what I want to change it to though. Let's see what we've got. It's been a couple weeks. See if they've updated it. No, it doesn't look like they've updated it. All right, what's trending? Same stuff. Huh. Let's go to page 2. Oh, these are better. Light ultramarine blue. It also does CMYK. They can either do the RGB code or the CMYK code. And CMYK color would be the command for that. Okay, so right now, there we go. Now we want orientation. So I want to plot arrows on this. It's going to be part of the plot style. Then the arrowheads command. I want 4 arrowheads on this. So I'm going to have to list out 4 of them. So all 4 will go inside braces, and then each pairing will go in braces. So each arrowhead has braces. The first value that you put in gives you the size of the arrowhead. Second value is going to give you a position. Where on the graph do you want it? Size. In order for this to work, I have to add one thing at the end. I'm saying line as an arrow. And there are the arrowheads. I can probably adjust these positions to be more of where I want them. Oh, that definitely didn't do what I thought it would do.
The numbers for the arrowheads will change depending on the font, like.
I typically use the same size of 0.05, but yeah, positions are gonna, it's wherever you want to put them. That looks better. But why are these still there? Oh, who knows? Whatever, doesn't matter. Get the idea. All right, so that was for 0 to 2 pi. By the way, what kind of shape is that? It's an ellipse, right? Circle is just a special type of ellipse. Remember, you have the semi-major and semi-minor on the ellipse. Next up was 0 to pi. I actually don't need all of those arrowheads now. Looks like I can get rid of the first one. And the middle one. And I deleted something by accident. What did I delete? What did I? Right. Oh. I didn't delete anything. I didn't delete the opening brace. That seems to look fine. Then they wanted minus pi over 2 to pi over 2. What I have to do is change that, see how that looks. Arrows kind of look nice where they are, so. There we go. Looking at the parametric curve given by secant t tangent t for negative 1.5 less than or equal to t less than or equal to 1.5. Just change the color. For now, let's just leave those arrowheads where they are. Nope, I'm gonna have to adjust them. I did 0.4 and 0.6. Now look how tiny those arrows are. So let's make the size 0.1 instead. See how that looks better. Now that curve is boring. See if this one's more interesting. Doesn't look like it. 2t plus 3, t squared minus 1. T goes from -2 to +2. T plus 3t squared minus 1. -2 plus 2. What color? Says supreme in it. Oh, those arrows are not good. Try 0.2 and 0.8. Let's see what that gives us. That's not bad. Nah, that curve is really boring. Okay. At this point, I think I'm just going to drop the arrows. Just get an idea of what these curves look like instead of a direction. We're gonna look at t minus sine of t, 1 minus cosine of t. Right, but have some fun with this one. I'm just going to just show you. Over the intervals they gave. I can't remember how random integer works on here. Perfect. 256, and I want 3 of them. This could be dangerous because I have no idea what colors are going to come out. That's half the fun. Looks like brownish. So that is 0 to 2 pi. I'm going to do 3 pi next, even though they wanted me to do 4 pi. And this is where we're going to have fun. Okay. So what does it not like? Oh. I think it doesn't like the fact that it's 0 to 0 for the first step. That would be my guess. That's sad. But I can't have it start at 0. Okay, so what I'm gonna have to do. Should be good. This is what happens as you let your domain extend out, and now it just stopped. Okay, why did you stop? Does anyone know what this shape is called? Hope this doesn't overload it. This may be a bad idea. We're going to find out. I'm willing to risk Aiden's grade on this, though. If this crashes, my PC is going to get a 0. It's not my grade, right? So I'm not worried. That's going a lot faster than I wanted it to, but whatever. Serves the purpose, right? Congratulations, Aiden. My computer is strong enough to handle this. This is called a cycloid. And so this gives you an idea of how the shape is affected by the domain. This is where we start to get into some of the really cool shapes. Right, with parametric equations, you can now get some really cool curves. Ones that you definitely cannot get just by functions. Two curves in one. First, we're going to look at positive, and we're going to look at all the positive values. Then we'll do the negative values and compare. And I think I'll also do the manipulation for these as well. Obviously, I won't go out to 100 pi. Maybe go out to 10 pi or something. Let's you for right now. So we had 2 cosine 2t plus cosine of 2t. I'm sorry, it was cosine of t for the first one. Two sine of t minus sine of 2t. So there's the shape. What happens as I manipulate the domain? Nothing. It just finishes out the curve and then it just continues to trace over it. Ah. What I could do is manipulate constants though. But I have other problems that deal with that, so I won't worry about it. Now what happens if the 2 becomes a -2? All of the 2's become -2's instead. Be a sideways apple. Missing its stem. So the next problem replaced the 2 with a 3, and again, plus or minus. So see what happens if we just adjust that. Giggity. So by making it 3 instead of 2, we got almost like a diamond. Now, what's going to happen if instead of 3, it's -3? We get this. Which for some reason I imagine is like an open toilet seat. I imagine that is the axis is the hinge. Right, so the previous shape, both of them together were called deltoids. I don't have a shape written down for this one. Makes me sad. But I do have one for the next. Instead of 3, let's do 9. Oh, actually, that's not the problem I wanted, but let's just take a look. Like one of those comic book owls, right? The one I wanted to look at, I think that becomes minus. Yeah. So it's minus cosine of 9t instead of plus. Hope this color is appropriate. Kind of. This is an epicycloid. Again, just changing the domain shouldn't affect this. Yeah, it just replots over itself. Now for a weird one. Of course, all of the cool shapes involve trig. Told you trig is sexy. This is a hypocycloid. Oh, ending on my favorite color. Perfect. This is a hypotrochoid. Again, I'm fairly certain if I adjust this, it shouldn't do anything. Yeah. I have fun describing that as a function. There are a lot of curves that we can now describe and examine thanks to parametric equations. Move the slope right at that point. Remember how you find slope of a curve? It's just the slope of the tangent line at that point. But what is slope of the tangent line? What is it? Derivative. Specifically, dy dx. We're now going to look at how to find dy dx of a parametric curve. So we can find slope of any curve. Or slope of a curve at any point. Area of that loop. How do you find area? Integral. So we're going to be now finding area for parametric curves or parametric regions. Do surface area too. No, I do not. And I don't even cover area in the problem set, but I'm fairly certain it is in the video. Last. The length of that curve. Right. In other words, if you were to traverse that entire path once, what's the distance you cover? That's an arc length. So we're now going to also look at how to find arc length of parametric curves. That is all calculus of parametric curves, right? That all falls under a branch known as analytic geometry. For us, specifically, geometry of the plane. Now, just extend this notion to calc or to 3 dimensions, and that is how Calc 3 starts. Geometry of space. You know you want to load. Find dy dx and d squared y dx squared for the curve given by t minus sine of t, 1 minus cosine of t. Oh, what is that? Isn't that a cycloid? The derivation is in the video.
Since this passes the vertical line test, would it be possible to write it as a normal function?
Yes, you can. That is called eliminating the parameter.
Is
Right.
it possible for every
No.
parametric function that passes the vertical
Yes.
line test?
So any parametric curve that passes the vertical line test, you can eliminate the parameter right as a function y equals f of x.
How would you do it?
Solve t for x, and then plug that into the y equation. Right, so x equals t minus sine of t, you'd solve that for t in terms of x, and then replace whatever you get into the t and the y, and that'll give you y equals f of x. That's typically how you eliminate the parameter. This case, it's going to be really difficult to do. You could probably try and write this x equals f of y. That might be easier. Again, I think I do some eliminating the parameter in the video. dy dx. Bless you.
Thank you.
Dy dt over dx dt, or whatever your parameter happens to be. I'm going to shorthand this. Perfect, OneNote just crashed. Did I go over dot notation already in this class? Well, 2 of you should know it, because I did do it in Calc 1. Also, if you've taken any kind of physics courses, you should know the dot notation. Dot notation just simply represents derivative with respect to time. Right, obviously we do that a lot in physics. We don't always want to write d something dt because we're lazy. Right. Physics, number 1 law of physics, everything wants to be in its lowest energy state. So the universe is lazy, so why should I be any different? Embrace the laziness, it's in your nature. Another favorite law of mine in physics is entropy. Basically, the universe wants to be chaotic. So whenever your parent yells at you for a messy room, just go, it's entropy. Law of nature. Can't overcome it. Didn't really work on my wife, so I tried, didn't work. What is the derivative of the y component with respect to t? Sine what? Sine of t. Derivative of the x component with respect to t. Minus cosine t? You're missing a term. One minus cosine t, right? Derivative of t is one. There's dy dx. We've been writing dy dx as a function of x up to this point. This just happens to be now dy dx as a function of t. Still gives you slope of the tangent line at a point. The only difference is you now have to find the corresponding parameter for that point. Right, so it's going to be t equals something instead of an ordered pair xy. But I may not give you the ordered pair. Or I may not give you the t. Or I may give you t, or I may not. I may give you the ordered pair. You'd have to be able to take that ordered pair and find the value of t for that point, which is not difficult to do. Have an example of that. Let me think of a point. Oh. That'll work. 0.00 corresponds to what value of t? Right. Well, remember that the parameterization gives you x comma y, right? So we need a value of t that makes t minus sine of t 0 and 1 minus cosine t 0. The easiest one to solve for is y. That would mean cosine t has to be 1. Which means t is what? Is that the only possibility for t? In order for cosine to be equal to 1. 2 pi, what else? Any multiple of 2 pi. Of those solutions, you also have to have t minus sine of t be 0. There's only one solution that satisfies that, and that's t equals 0. Right, because wherever cosine is 1, sine is 0. And because that t in front, that t minus, that first part is just going to be whatever t is. So if it was 2 pi, you'd have 2 pi comma 0. That is how you determine t. The reverse is also true. If I give you t, but you want the ordered pair, you just plug the t I give for you in for c, and that gives you the ordered pair of the point. All right, so again, if I did 6 pi, the point would be 6 pi 0. You plug it into c, yes. Right, so if I gave you t equals 0, and I said, what point does that correspond to? You just calculate c of 0, right, which would be 0, 0. Second derivative. I don't remember if I derived this in the video. It's been a couple years. If not, I leave it as an exercise. Again, I'm using the shorthand because I really don't feel like writing DDT 5 times. We know x dot. What is y double dot? So in other words, the second derivative of y with respect to t. What is x double dot? And we know what y dot is. And all over 1 minus cosine t cubed, right? X dot cubed. Simplify that. The cosine minus cosine squared minus sine squared. How does that simplify?
Sine minus.
How does that simplify?
-1 over 1 minus cosine t squared.
There would be your second derivative with respect to x. Second derivative of y with respect to x. Keep in mind, that is not C prime.
Show us
Which one?
the second group.
Lever D concavity? I think. To be honest, I don't know because I've never done geometric interpretation of a second derivative for parametrics. I've only ever done the first. But again, I've worked with vectors, so I've always just done first derivative vector, second derivative vectors, things like that. If I had to guess, I'd guess concavity at a point.
So why is it that rather than just being quotient rule, it has an extra dx in the denominator? Or the dx dt?
I leave that as an exercise for you to derive. If I didn't do it in the video. Again, it's been 2 years since I did it. My guess is because it's technically implicit differentiation. It's probably where the extra x dot in the denominator comes from. Yeah, that's exactly what it is. It's because you have to do it implicitly. Right, you're doing d dx of dy dx. Which is implicit. But again, I'll leave that. It's the beautiful thing about being the instructor up here. I can just go, leave it to the reader. So, interestingly, the whole point of finding dy dx, right, would be to find slope of a tangent line at a point. C prime of t does the same thing. With some extra steps. You have to find the equation of the tangent line first using C prime, and then you can get slope from that. You will cover that in Calc 3. Don't know why, because it's really stupid simple. You just take the derivative of each component, and that's your C prime. Again, don't know why it's not in Calc 2, why they say that for Calc 3, but smarter people than me came up with the calculus layout. Now looking at the curve, e to the t cosine t, e to the t sine t. We want same thing, dy dx and d2y dx2. If I remember correctly, this curve is actually very boring. Even though it looks like it'd be interesting, it's not. Now, so that is read second derivative of y with respect to x. Right? Technically, even though we write it that way, what this really should be, and this also, so that is technically d dx of y. This is that is read as second derivative with respect to x of y, right? So that d dx is an operator. The d squared dx squared is an operator. Specifically, it's the second differential operator. We just write it in the numerator to save space. Looks cleaner. But this is technically what it is. Right? And of course, remember, this is not the same as that. Right? This would be, first off, this as it stands doesn't make sense. Right? Because it's just an operator squared, which makes no sense. That would be dy dx squared, right? So that's take the first derivative and then square it. And of course, that's also wholly different from that, right? That's the derivative of y squared. Right. All right, so dy dx is y dot over x dot. What's y dot? Well, y isn't sine of t. You forgot a term. All right, so you want that derivative with respect to t. Which is what? How'd you get it? Not chain rule. Chain rule is something different. Chain rules for composite functions. Product. What is x dot? That can, of course, be simplified. Or if you're like me and you want to be symmetrical, you just rewrite the order of the numerator. Doesn't matter. This is just evil. All right, x dot we have. It's this. Y double dot. You now have to take the derivative of the numerator. Product rule, sum rule, product rule. It's going to have 4 terms, which hopefully simplifies down to 2. I think it does. Then you have to FOIL. Oh, and by the way, once we get to x double dot y dot, same thing. But we want to be in the lowest energy state possible. I'm going to use Mathematica. I've now stored my x and my y. Yeah, it should be x prime, because I knew that wasn't right. That's better. There's my second derivative with respect to x. And then what you do is just go like this, and you go. Someone asks you, well, how'd you get that so quick? You just go, it's obvious. And if it's a really good friend of yours, you just go. And if you can't see that, then you're too stupid to be my friend. It's actually a really good friend, you're going to get slapped or punched. If they just cry and accept your proof, then you defriend them. I'm going to write it without the negative exponent. So there is d squared, dx squared.
Could you go back to the mathematics just for a second?
Can I? Yes. I'm physically able to go back. Apparently I can't. It doesn't want me to get back. Oh, come on. There we go. It's just a simplify command. You can also just put that in without the simplify, but it is not going to give you that. It's going to give you the unsimplified form, which looks hideous. Looks absolutely terrifying. You have access to technology, use it. Now we're going to go ahead and actually find the tangent line to the curve. Root t, t minus 1 over root t, at the point where t is equal to 4. Remember what the equation of the tangent line is. That means there are what? 3 things we have to find. We have to find that y naught. We have to find dy dx at the point x naught. And then we have to actually find x naught. Well, dy dx at the point, oh, that's easy to do. That's going to be dy dx when t is 4. Which is y dot of 4 over x dot of 4. What is y dot? You don't have to evaluate that for, just tell me what y dot is.
Two T's.
For sanity, I'm going to write it with a negative exponent because it's a complex fraction. What is x dot? What is it? You're very close. Positive. This simplifies. Two root t plus 1 over t. When t is equal to 4, Get a slope of 9/4. No, we don't. Seventeen quarters. Tangent line would be y equals, what is y naught? Hmm? No, you're thinking of, if I put it in the form y equals mx plus b, b is the y-intercept. Y naught would just be the y coordinate of the point that we're at. How did you get negative 3.5?
Minus 1/.
Right? How's that negative?
Oh, sorry, just 3. That's one.
I wanted to make sure it was an arithmetic error or not. 7/2. Plus our slope. What is x naught? 2. Now we just simplify that. Seven halves minus 17/2. Is minus 5. There's our tangent line. At the point given by t equals 4. Questions so far on parametric equations? Aiden, how'd you get 7/2?
Plug in 4 to the original factors that you have. For the plumbing.
Right, specifically the y component, right? The y of t. Right, because remember, this is x of t comma y of t, right? That's also where the 2 came from. Any other question? So we're not quite done with the problems on parametric equations. There's 3 left. I'm perfectly okay with that because it's the end of the semester. So if I have to go into a little bit next week, I've got no problem with that. So the plan for Thursday is to finish up those 3 problems. Then you'll take your quiz on this stuff. Then we'll start polar coordinates and we'll just get as far as we can in polar coordinates. Who knows, you might get lucky if I can finish polar coordinates, you get 2 quizzes in one day. I know everyone's excited about that. If not, it will not take me long on Tuesday to finish up polar coordinates. Right, because I should be able to get through a lot of polar coordinates on Thursday. I will let you know next week once I've made a decision. So see you all on Thursday. I actually went over. For some reason, I thought we were done at 6:45.